I'm Brittany Duggar. Again, great to be here. The title of my talk is Many Faces of Dementia and Why They Matter. And with any talk, it's a journey. And I always, just like a table of contents, here's our map for our journey today together. I'm going to be talking about the many faces of dementia, going across a variety of topics, which includes clinical presentation, so those outward signs and symptoms versus underlying disease, what's in the brain. I'll be talking about disease stages. People just don't wake up with dementia. It's a process. It's not like you go to bed on Tuesday and all of a sudden you wake up Wednesday with full-blown dementia, although maybe some people do, but usually it's a process. I'm also going to talk about concomitant pathologies. So with dementia, there can be more than one disease present in the brain at one time. And this is a very important concept to understand, especially if you're on the clinic side trying to give diagnosis, but we always want to give one diagnosis for one symptom. And then I'm going to be talking about some demographic variables. So depending on cultural, socioeconomic status, these can potentially have risks for certain types of dementia. Then I'll be shifting gears because it's not just about understanding these many faces of dementia. We also want to have tools to do that. So I do a lot of things with machine learning, and I'll talk about that and how we develop a pipeline. It's not just the fact of one output result that you're going for. Oh, look at all these beautiful graphs that agree. It's this pipeline of you have a starting material and what do you want from the end. And then this interpretability. So again, what the machine is doing, how the machine is thinking to open up that black box. And then finally, I'm at the University of California Davis Alzheimer's Disease Center, UCD. And we do have some resources that I'd love to make sure you guys are aware about, because we share things. We're scientists and we like to share, especially knowledge, but we also have other resources as well. So how did I get here? Well, how this all started was I had two amazing persons in my life, and they were both diagnosed with dementia. They're my grandmothers. Here in this photo right here is my grandma Duggar. So this is my dad's mom. And then I have my mom's mom, which is my grandma Moransky. And so both were diagnosed with dementia when I was fairly young. But to me, I was frustrated because they were given this diagnosis of dementia. But to me, they had very different disease presentations. So for example, my grandma Duggar couldn't remember who I was. She would always hold my hand and tell me to say hi to her granddaughter who I go to school with. That's what she would tell me. At the same time, she couldn't remember who I was, but when she went to church, and this is a church she didn't go to till after she was diagnosed with dementia, and she would sit in the same spot every Sunday. So to me, you know, and this is in an age before the internet, so I couldn't really Google anything. I don't think Google even existed, so that kind of dates me. But understanding that concept of, okay, I'm frustrating that she can't remember who I am, but yet she can sit in this spot at the same time. So I was very frustrated with that. On the other hand, my grandma Moransky, who was also diagnosed with dementia, she didn't have so much memory problems. It was more of hallucinations. So she would converse with us about how she had breakfast with the TV news people, how they came over and sat at her table and they had just a great time talking about the news of the day, which we knew wasn't true. But at the same time, both were diagnosed with dementia with two separate disease presentations. So to me, this was befuddling. I was very frustrated with it because I didn't understand that. But now, going into this field, the definition of dementia, which they both had, right, is a decrease in activity of daily living and cognitive impairment. So they both technically had that. But that being said, you have this outward clinical presentation of dementia, and you have this understanding of the underlying cause of that. Just like if you have an outward sign of a high fever and a cough, is it COVID? Is it the flu? What is it, right? You have all these underlying causes that it could be. So with dementia, we have this long list of different causes of things that it could be that's aiding with that clinical presentation. And then with that, these dementias, because there's also these other outward signs, these clinical symptoms that can happen. So here's just a list, and I apologize because I know it's in the afternoon and I'm showing you a lot of text on the slide, but just trying to think of the best way to represent this is we have Alzheimer's disease, which will be dementia, but that's mainly forgetfulness and word finding. You have dementia with Lewy bodies, which has that hallucination component. And then you can kind of go down the list of seeing there's these similarities and differences. So as clinicians, it can be probably pretty tough to diagnose. That's why you hear the terms like probable and possible when you're referring to these diagnoses. And so when we deal with this, so we have these clinical signs and symptoms, and clinical science is not an exact science. A clinician can have only so many tools to work with. And so what we did is to try to understand these concepts is we compared a clinical diagnosis before death to the neuropathology. So after the person dies, we examine their brain. And in this paper, we focused on Parkinson's disease. And again, this is a lot of text, so I just highlighted this sentence right here, is if a person was clinically diagnosed with Parkinson's disease less than 5 years before death, the accuracy, and I'm using that term lightly, right, because clinicians only have so many signs and symptoms that they can use. So when that Parkinson's disease actually matched up with the pathology, it was only 53%. So imagine having a devastating diagnosis like Parkinson's disease, but the clinician was right, again, using that term very loosely, 53% of the time. And so when we talk about these diagnoses pathologically, so we really only can diagnose a person once they pass away, which is awful, right? We have to wait till somebody to die to get their diagnoses. There's been a lot of advances with imaging and people are looking at blood biomarkers, but still the gold standard has been pathology. And so when we classify these diseases, we classify it based on abnormal aggregates of proteins. So here's just an example of an abnormal aggregate of amyloid beta, which all of us have these proteins in our body, but what happens is they fold up on each other and then they remain and they can't be degraded. And so with here, you have the amyloid plaque in Alzheimer's disease. And so I can stain the brain for certain things, actually amyloid beta to reveal. So here's an immunohistochemistry stain of amyloid beta, and here's thioflavin S, but just see how the shapes look, right? Another aggregate is tau, and tau can be found in a lot of different diseases. It can be found in progressive supranuclear palsy, in a pathology known as tufted astrocytes. So we'll see these in the brain in certain anatomic locations. In cortical basal degeneration, there'll be astrocytic plaques, again, aggregates of tau and astrocytes in certain locations of the brain. There'll be PIC bodies, so these round bodies in certain areas of the brain. And then last but not least is that neurofibrillary tangle. And with these are just a couple of different stains that are used to reveal, but hopefully you can appreciate the shapes of these are very, very different. So this is how we're classifying this as a neuropathology researcher. I look at the brain, I stain it for certain things. It reveals these pathologies in certain brain areas. I go through like a matrix. The best way I can describe it is like organic chemistry, right? You have all these chemical processes and you create your synthesis. I create my synthesis for diagnosis and give a diagnosis. And then last but not least is abnormal aggregates of alpha-synuclein, and these are Lewy bodies in dementia with Lewy bodies. And again, all these proteins you and I have in our body. We have alpha-synuclein, we have tau, we have amyloid beta. It just those processes go awry either by post-translational modifications, cleavage products. You have all these things that are hypothesized to go awry to create these aggregates. So that's why you think of a lot of therapies that are focused on that kind of thing. And so a lot of studies over the years have aided in understanding this link between clinical symptoms and this underlying pathology, right? Like we study, like at the Alzheimer's Disease Center, we study how people are living, we give them all the cognitive exams, take their demographics, take down their medication, family history, we have all that, and then we can look at their brain and we understand clinical path correlates. The issue with that, though, is many studies typically focus on one diagnosis. There's a really important thing of understanding all the different diagnoses that can happen in the brain. So understanding that synthesis as well as the location. So it's not just that tau, aggregates of tau are there, it's where are they? Are they in the hippocampus? Are they all the way in the cerebellum? Like where and how much? So there's all these different aspects as well as disease states. And then the other huge important thing, which I think I'm preaching to the choir here because you guys are doing a lot of work in this area, is cohorts are mainly consist of upper middle class white Caucasians. So when we're focusing on a cure or a prevention of these diseases, we're only focused on one sect of the population. As you know, we're very, very diverse in this country and in the world. So if we're just focusing on white people, how do we really understand this importance of social, cultural, economics, and behavioral characteristics? And I'll get into that, and I'm going to use race and ethnicity, but just to be mindful, I'm not saying that that entire race or entire ethnicity, you know, that's the biology is the underlying thing. No, it's most likely a lot of these other factors where we have to use race and ethnicity as a proxy. Because when people come into the clinic, it's not like, oh, what was your income? Where did you live when you were 5 years old? We don't have a lot of those detailed data, so we use these things as a proxy. So I'm going to try to be as cautious as I can when approaching that, because I am a white female, right? I'm not Hispanic, I'm not Latina, you know, I don't have those identifications with me. So if anything, just let me know if I overstep any boundaries. And so I talked to you about these things, but how common are they? I could sit here and preach that, oh, you got to be aware of these concomitant pathologies, right? Like, oh my gosh, they're so awful. But like, really, what's their frequency? So we did a paper a while back just looking at, say, these are a whole bunch of Parkinsonisms. So you have Parkinson's disease, dementia with Lewy body, progressive supranuclear palsy, multiple system atrophy, and cortical basal degeneration. And for sake of purpose, I just have Alzheimer's disease here because we can focus on Alzheimer's disease. So with cases that had Alzheimer's disease, and then they also had, say, dementia with Lewy bodies, right? So when we look at this, you see that there's a large overlap. So sorry, I have to reverse that. So it's cases with dementia with Lewy bodies who have Alzheimer's disease. That's what it is. Okay. So with each one of these, how much is the Alzheimer's disease overlap? Are you following me on this? So if you have dementia with Lewy bodies, you're pretty much going to have over an 80% chance of also having Alzheimer's pathology. And even look with Parkinson's disease, it's almost at 40%. So all this stuff is very, very important to understand, because say you develop a drug and it's to treat dementia with Lewy bodies, to go after that alpha-synuclein, but then they also have tau and amyloid in their brain. How are you going to deal with that? So this is a very important concept to understand these concomitant pathologies and how frequent. And so the next concept, so just to switch, we talked about concomitant pathologies. Now let's talk about disease state. So a lot of people, you know, you talk about full-blown dementia, but again, you don't wake up with that. You kind of start off, and it's been shown over the years that pathology happens before clinical onset of disease. So you'll have these plaques and tangles being aggregated in the brain well before the onset of clinical symptoms. And this is just a photo depicting this, is how we have a prodromal mild cognitive impairment, and you see how the pathology spreads. And I almost look at this like a car accident. You have a car accident, but that traffic pattern can back up. But how much does that traffic pattern back up over time? So you have these aggregates or car accidents that'll happen in certain areas of the brain, and then they'll back up into certain other anatomic areas. And then finally, when you get enough of a traffic jam, you're going to have a dementia. And what of diversity? I'm sitting here talking to you about, like, most studies are of white, you know, Caucasians, but show me the data, right? I could claim that there's voter fraud, but show me the data. Like, what are the data? But before I do that, this is always a sensitive subject, because many studies will have recruitment biases, and a lot of different sects of people, there's been a lot of mistrust with the healthcare system, with providers as well as researchers, and there's a lot of socioeconomic confounders. So I do want to bring that to light before I get into this sect of research, because these are very important things, as you all know, because you're studying similar aspects that we should definitely take into account when embarking on these studies. And so with that, if we just look at, so what I did was I pulled data from the National Alzheimer's Coordinating Center, which is a compilation of data across 32 different Alzheimer's disease centers. And there's questions and what's called the intake forms. These are just common intake forms, and people declare their race and ethnicity. So hopefully you can, even though it's late in the afternoon, a lot of people in the NAC database are not Hispanic and they're white. This is a problem. Even within our UC Davis Alzheimer's Disease Center, because as you're probably well aware, even within Hispanic Latinos, there's a lot of diversity even within that group. And so within our UC Davis Alzheimer's Disease Center, even with that, a majority of our cases are going to be from Mexican, Chicano, or Mexican American origins. We don't get a lot of other sects of this large diversity of Hispanic Latino community. So even when we come up with these results, they shouldn't be applicable to everybody from that sect, right? It's this whole concept of individualized precision medicine. And so again, I talked to you about these studies, but does this really matter, right? Okay, yeah, so what? There's different ethnicities and race. But are there differences in these clinical pathological diagnoses across demented African Americans, Hispanics, and non-Hispanic white decedents? And so just to show you a demographic table, so these are the demographics of the participants, the characteristics, and again, I know it's late in the day, just to highlight some of the differences, there were differences in education, as well as certain clinical factors like hypertension being more prominent in certain groups and not others. So just having those concepts in your head when you see these next pie charts. So here are the pie charts on the clinical pathological diagnosis, and hopefully you can appreciate that certain diagnoses are very different, especially in the Hispanic group. So in people that identified as Hispanics have more cerebral vascular disease when compared to especially non-Hispanic whites. So again, this is really important. So say I find a drug for Alzheimer's disease and I'll be like, oh, I'm gonna just give this to everyone. Okay, and I'll give it to everyone across, but what if I'm giving it to a sect of people that also have, on top of Alzheimer's disease, cerebral vascular pathology? How is that drug going to work? How is their treatment going to work? We have to understand all these differences to get the right treatment to the right patient at the right time. And now what I'm doing to delve a little bit deeper, and I wanted to show this slide because I think so many times people like show you a graph, right? Notice there's no graph on this page. They just show you a graph and, you know, they kind of gloss over it. But this next study that we're embarking on, and we're about 2 years in doing all these data, involves so many different people from so many different backgrounds. So hopefully you can appreciate all these different people. And these are just some of the main players, not showing some of the background workers as well. And even undergraduates are involved in this, which is so awesome. And what we're doing is we showed you those pie charts, right, of the overall diagnosis. We want to delve a little deeper in looking at this underlying iceberg of these locational aspects of pathology and other clinical parameters. So to do this, we're going to be examining over 200 cases across 3 institutions. So trying to understand a lot of different sects of Hispanics, including those from Colombia, living in Little Dominica. We have from UCSD, so University of California, San Diego, as well as here in Sacramento. So we've tried to capture some swaths, it's not perfect, right? But we're doing what we can. And with that, we're examining over 5,000 microscope slides to see what's the same and what's different. And so with that, I'll have a pause moment because that was a lot of information. And if somebody wants to check the chat, then I can answer any questions so far. Or if people can answer questions that they feel like I might have missed something, because I'd love to learn from you too.
So, Brittany, this is Gladys. So you are telling us that we know, I mean, even the genetic data shows that the differences between the race is not that much, even at the genetic level.
Mm-hmm. That's why I try to stay away from those terms, and I use the term proxy because there's so much, the socioeconomics, there's like so many underlying things that are going on.
Hispanics or Latinos, Latinx are a mix. So whatever difference is going to be kind of ironed because of a mix. So there is not a unique. But you are telling us that accumulations of certain type of pathology is really different, meaning that the differences in the characteristics of the disease in the brain actually might be a reflection of the living conditions and exposures of the people. Is that right? Is
Yeah,
this your?
potentially. And there's a lot, I'm not an epidemiologist, but I know there's a lot of epidemiology studies that have shown this, that there's a higher rate of vascular disease like
Mhm.
hypertension, hyperlipidemia, obesity in Hispanics, Latinos, Latinx persons when compared. But as you know, it depends on who you're studying will drive your data. So that's why I'm trying to expand this and understand, like including groups from Columbia University in New York, as well as University of California, San Diego, to increase, because that initial cohort, we only had 35 cases. And to call
Mm.
that representative, yeah, but it is what it is. And that's why we want to investigate it more to make sure that we can advise the
So
best.
the people from Columbia University in New York are going to be most of Caribbean
Yep,
descent.
that's correct. So they're from Dominican Republic, hence
And
little
Puerto Rico, yeah, the two. But probably the people that you have is Mexican Americans,
Yep.
right?
And that's
Or
one of the things that we're testing, because when you think of even those two sects, and I used to live in Puerto Rico for a while, and understanding the migration patterns of how Puerto Ricans come to the United States versus those from Latin American countries. They can be very different. And how then does that determine access to healthcare, occupation? So there's a lot of underlying factors that could drive that. So it'll be very interesting to see. And there's been some work with epidemiology studies too, showing differences between, say, like people of Caribbean Islander versus
yeah.
Mexican descent. Mhm.
Would you say that these populations are? I mean, are your individual subjects are coming from urban areas or semi urban areas in contrast to rural?
I don't know that completely. I know that there's people that we collaborate with that are doing some really cool stuff with like neighborhood atlases and GIS. I know, what is it, Amy Kind has been doing stuff like that. I don't know if you're familiar with her work. She's up at
Yes,
Wisconsin. Yeah, the neighborhood atlas is such a great tool to try to understand those kind of disparities there.
because our population here it's mostly Mexican American, but this is ru- it's semi-rural, but boy, it looks rural to me. So there are, like the agriculture, industrialized agriculture business, the contamination of the Rio Grande, and all these things that
Yeah, there's so much and thank you for bringing that up too. I didn't even touch about like environmental factors, right? Like occupational hazards of, you're in the fields working with pesticides, all this kind of stuff. How does that play a role in everything?
yes. So I'm just wondering, how much valuable will be for us to and for the field to actually being able to have our brain study by, you know, like you are studying other brains from other areas, because in fact it is possible that um, the access to populations like these ones is just reduced.
Well, all of our, and this is even with men, women science too, like even though I'm talking about race, there's been studies that have shown, like, and it's great. I think John Oliver gave such a great segment on this, is like women medicine, right? And like how a woman heart attack is different than a man's heart attack. It's such great data. And this thing of all these disease scales. So I just talked to you about those disease stages. All those are based on European white men, and no
Mm,
one's, and that's my grant right now, is like, I just like, hey, we've done these disease scales, Brock stage, Thal stage, all this kind of stuff, and you go back and look at the original papers, and they're like people from Austria, Germany, kind of white men. Here's your
mm,
cohort. Oh, look, this is how the disease progresses. I'm like, wait, this doesn't make sense. Like, where's your diversity? Like, what if the disease is different? Not saying that it is, but we just need to have a diverse cohort. Just like when we're testing for COVID, we need a diverse cohort to see how the medication is going to react across numerous types of people. So
exactly.
that's where it lies. So that's why I'm just really excited to study, but it's a fine line, right? Because I don't want to go down that route of saying the biology is different. I really don't want to do that route, because then just by saying that creates these levels of superiority, which there's not.
Exactly. No, that's very important, and I appreciate that you have thought about these implications, and there is something called bioethnicity, in which people are really trying to find markers for ethnicity, and there is
Yeah,
not just
I don't. Notice how I didn't show you any genetics, because I take it if somebody fills out a questionnaire and they say that they're Hispanic, then they're Hispanic to me. I'm not going to run their genetics going, well, you had this percent of Amaral Indian and blah, 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 blah. So then we need to move you over here.
Okay, thank you.
Yeah, no, thank you for bringing that up. And hopefully I got that across, because this is something near and dear to my heart. When people put labels on me saying where I should fit into a box, I'm like, no, don't tell me where I should fit. Okay.
Governor,
Any other questions?
yeah, I have a quick question. In one of your figures, maybe I misinterpreted, but does it look like tau is starting in like the tectum area? Is that one of the first areas, or am I maybe I it was quick, but
It's definitely just a diagram. So this is locus ceruleus. Yeah. So I'm a firm believer that the locus ceruleus gets hit first and then kind of goes. So I'm glad that you caught that, because a lot of people think it's hippocampus, but there's a lot of data that's showing that locus ceruleus gets hit. Even the olfactory bulb. So olfactory bulb, which they didn't color here, they colored here. I guess this is their olfactory bulb. So when I've looked at cases in my over a decade looking at cases, if I'm going to screen, I'd look at olfactory bulb and locus ceruleus to see if tau's there. And then more often than not, it'll be in these subsequent areas.
okay. Do you see anything in the dorsal part of the midbrain, for example, or not really?
Oh, it's good that you bring that up. So with the locus ceruleus, there is a rostral caudal gradient that happens. And when you think of the connectivity, so with the locus ceruleus, the more rostral part are going to connect more to the cerebrum, and the more dorsal part is going to connect more down to the spinal cord and everything, right? So in Parkinson's disease, the locus ceruleus is affected as well, but it's affected across the whole axis.
Mm-hmm.
So that'll be degenerated as well. But in Alzheimer's disease, and it's a sampling issue, right? So if you're going to sample more rostral, you're going to see that degeneration.
Okay. All right.
Does that help a little bit? Yeah. So it's not just, oh, it's only locus ceruleus. It's even within the locus. It's just like I could say Texas. You're like, whoa, 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 whoa. Rio Grande is a lot different than Austin, right?
Yeah.
Okay. Thank you for catching that. Okay, moving on. Shifting gears now. Everyone good? So now getting into this machine learning stuff, which is a little bit of a jump. That's why I like the gear shift to have that pause moment to jump. And we're going to be talking about developing a pipeline. So the first is you got to identify the problem. So this is a lot of different ways that we assess pathologies. We can do semi-quantitative scores like none, mild, moderate, severe, sparse, moderate, frequent. We can do positive pixel counts where I can trace an area and say, I want to detect this color brown, what's the percent area? You can do things like stereology, which is systematic random sampling to do counts. And you could just do a count, right? So these are just some examples of how you can do some neuropathology. But most of these, pretty much all, require a certain level of expertise, training. There can be inter-rater reliability issues. So think about that semi-quantitative score. What I call as moderate, somebody might call as frequent. It can be very time consuming. If everyone's ever done stereology, it takes a while. And it can have limited statistical power. So if you're only dealing with none, mild, moderate, severe, and everything's severe, how do you do a correlation? Because everything's asymptoted off already, because disease is just so confluent. And then it can be affected by the tintorial properties of the tissue. So if anyone's ever done staining or bright field staining, that brown staining, blue staining, you can have batch differences. So how do you do this if you're doing positive pixel counts? So over the past decade, I've been trying to think of better ways to get more out of our brain tissue. We have all these brain banks across the country, slides are already stained. How can we get better data quicker in a wonderful way? And so we're in the age of machine learning. Here is just a great example of, I can take a photo of myself. This is using Google Arts and Cultures app. I own no stock in Google. Okay, there's my disclosure. and I can take a picture of myself and it'll tell me what famous painting I look like. And so this one, it tells me I'm a young woman and it's a 65% match. And this was just yesterday. I think I took it in the afternoon. And on this side, it tells me that I'm an old woman at 67%. So it's 2% more. I'm an older woman than a younger woman. Same image. But then I really like this middle one, even though it's at 62%, it says I'm a lady. So even with one picture, using these machine learning algorithms, I can get a bunch of different interpretations of what my face looks like. So thinking, could we use these similar processes with pathology? So with our brainstorming framework, and this is something that I've done a lot of cross-disciplinary dialogues, especially for those that are on this presentation right now that want to do a collaboration, that don't know how to start. You typically have two fields that are intersecting. You have somebody, what's the value of the system and what a certain thing can do. And so with machine learning, we have to first understand what machine learning can do. And then the value for the healthcare system, and we need to find that intersect. And usually that intersect is we have to think of machine learning tasks, and I can't emphasize this enough, as it's automating a task rather than a job. So a lot of people are like, oh, machine learning will diagnose this disease. But diagnosis is a job, is a whole full entire process. That how can you break that down into simple tasks? And a task to operationalize that is something a human can do in maybe 2 to 3 seconds. That's what a task is. So that's what you have to start with when you're trying to develop all these things. And for value, even though you can do it, as we do with a lot of science projects, because it's really cool, we have to think of what are our main pain points in our domain. So my main pain point in neuropathology is I have to count a lot of things. That's a huge pain point. But how do we break this stuff down? And so with that, you have to create a dialogue. I can't emphasize this enough. With science, is a lot of times people say collaborations, but they're really not true collaborations. I really like to sit down with the team and we really have open discussions on how we can move forward together. And this just doesn't involve one type of person. With these collaborations, this initial collaboration involved a string of computer scientists. It also involved neuropathologists, clinical scientists, as well as statisticians. So think of all the disciplines that are represented just in this slide. And we started to talk of how do we move forward together to solve some of these pain points. And so what we did was we came up with this pipeline. So again, our starting material are these whole slide images, which we digitize using a slide scanner. So it's just that typical microscope slide. And we started with a single area, the temporal cortex, and a single stain. So again, starting simple with a single task. We then did, because a lot of these were archival, and we want to try to minimize variables to keep everything the same, we did what was called a color normalization, because over time, things can change, batch differences, all this kind of stuff. And then this is very important as well. These slide images are really big. Like each slide can be about 1 gigabyte in size. And so how can we partition that down into the most finite piece that we need to analyze? So we use what's called bounding boxes. So if anyone's ever logged onto Facebook, you know how they put a box over your face and they ask, is this you? We're using similar technologies to pull out objects of interest. So this automatic tile level segmentation to get rid of all the negative space. And then because we're doing a technique that's called supervised machine learning, so we want to tell the machine initially kind of what everything is, we have to have an expert annotate things. And so what we did was we created a custom web application for this, because annotations alone can be tedious. So how can we speed it up and make it fun? And so this is the platform that we developed. It's very simple. And if anyone's ever had to follow a protocol, you don't want to have a million different sheets. So we basically, on the web-based platform, we put the simple instructions. So you don't have to keep going back to an email to check, oh, wait, how do I do this? What's this? What's that? We kept no bells and whistles, just very streamlined. We even have keyboard shortcuts. So I don't have to come and click every time, because you think if I had to do that, that's time. So what if I do keyboard shortcuts? We also have, see how there's a crown? This is our gamified theory to make it fun. So based on how many things that I can label. I reach different levels and I get like a crown or I get a trophy. So trying to make it as fun as we can for that. And with that, I was able to annotate about 2,000 images an hour, which is a pretty good rate when you try to think of trying to get a lot of data, because with these machine learning algorithms, they need a lot of data from a lot of different sources. And then with that, hey, look, guys, this is our output for machine learning. And this apparently is good. Everybody understands what's going on here, right? These AUC curves and precision recall. Oh, it looks so pretty. But as a pathologist, when the machine learner showed me this, I was like, okay, this is great, but what does that mean? What's the machine looking at? Like, how is it determining what a plaque is? How is it determining what cerebral amyloid angiopathy is? And so we started talking about this interpretability. So there's a lot of papers that are coming out on machine learning, and they're showing these graphs of agreement, but really delving deep into understanding how this is working. What's the hypothesis? What's the mechanism? And so what we tried to do is first off develop heat maps, and this is based on probability. So when the machine, goes through all the data and everything, it'll spit out a probability, not necessarily a number. And from that, we created these heat maps to understand all the different pathologies that we have, and are they in the location that they should be? So with plaques, they're mainly located in the gray matter. So here we have here's white matter, and you see this dashed line, and then this is gray matter. So diffuse plaques are in the gray matter. That's where they should be. Awesome. Chord plaques, same. You might have a little bit because this is, you're looking at a three-dimensional something two-dimensional of a three-dimensional object. And then cerebral amyloid angiopathy, when you see, it's mainly located at the surface, which is probably all this could be leptomeninges here. You can see how this is kind of going in like a gyrus. So it makes sense that, but we wanted to take it a little bit further. And so what's the gold standard? The gold standard are these CRAD scores of sparse, moderate, and frequent. So are our scores matching up? And so hopefully you can appreciate they are, but also appreciate, especially like looking at this graph, like there's a large spread of things that are being called frequent. But then when we actually do the quantification, that deeper phenotyping, there's this large spread, which is really, really good to denote. We also do these other unique things to try to visualize what the machine is looking at. So these are called GradCam images. And this is this is the image. And just imagine like you walk into a room and you want to look for people. You're not going to be looking at the ceiling. You're going to be looking at a certain area to identify your object of interest. And so that's kind of what this is representing. So these white things on these image are representing what the machine is actually looking at to make its decision process. So when it sees this image, when it's trying to identify it as a core, it goes directly for the core. When it's trying to identify it as diffuse, it's looking up here, but it's also looking down here a little bit just to make sure, okay, I know that that's not there. And then when it's CAA, it's kind of looking at a lot of image area, right? But there is no CAA. So that's why it might be probably looking at that large. The other thing we do for this interpretability is we do what's called a feature occlusion. So we'll actually remove a small set of pixels from the image and see what happens. Like, can it still identify what it's looking at the image? So for here, if we take out this core, which is the signifying feature of a cord plaque, you can see how the probability changes. So the confidence scale definitely changes if we exclude these pixels in the middle. So with that, even though that was a great study, we had a great publication in Nature Communications, there was a lot of limitations. We only use slides from one source with one stain, one anatomic area, annotated by one expert. But the purpose of that first paper was not necessarily the most optimalist paper that you've ever seen. It was a proof of concept of the pipeline. That was the purpose. Like, can we make this pipeline from start to finish? And now we'll start to optimize it. So since that time, we have optimized it. And this is some great work that was led by JC Viscara at Emory. So we have collaborators at Emory that actually took slides from their brain bank and treated them as a holdout set, and were able to recreate our whole pipeline and get data very similar to our data, which was awesome. Like that's, even though we talk about science being reproducible, the fact that he just went off the paper that we published and all the methods, even though he had to update the code because there's different versions of Python and YOLO that were floating around, it's still the fact that he could recreate it in a separate cohort, which is really awesome. And he took it a step further. And remember how I talked about that disease heterogeneity? He was finding differences in plaque burden if a case had AD and TDP43. So cases with AD and TDP43 deposits had more plaques in the temporal lobe than pure AD cases not having that. So pushing that science forward of why we're doing this deeper phenotyping. We're also doing a project right now, which we're submitting this week. My fingers are crossed. And this is led by a wonderful graduate student at UCSF. So again, numerous collaborators. I'm not a machine learning expert, but there's graduate students that can help with this. So Daniel Wong's leading this, but we had a panel of experts that annotated images, as well as having images from 3 different sources. And we even had 2 novice annotators, which were my undergraduates at the time, do some annotations. So this not only looked at differences amongst annotators, but also experts versus novices, and then understanding images from 3 different sources. So trying to expand upon that to how generalizable is our pipeline. And we're expanding even a little bit more because one of my big things is how to create resources for people to do this. And so what we've tried to do here is slinging these really large images and having access to it. There's a lot of issues because they're so big. Like granted, yes, we could use, you know, AWS or cloud-based servers, but sometimes that can be really difficult when you're on grant money and cycles because that you're paying like by a subscription. And so what we did within the UC system is we tried to, and we're in the midst of doing this, is we created a server hub, which we're sharing our brain slides across institutions, which is really, really awesome to create not only these annotated data sets, but educational resources. So if somebody's like, oh, I want to see what an infarct looks like, hey, they can go over here and choose one of these files, and that's what you'll be able to see. So we're in the midst of building that. But as you can see, there's a lot of people involved in this. Okay, so I'm going to have another pause moment before I get into the last portion of my talk. Were there any questions with the machine learning stuff? Again, I'm not a machine learning engineer. I'm more on the pipeline aspect of things, trying to oversee that.
Could you talk a little bit about your sample size, or how many slides are in the brain bank, or how many brains? Actually?
Oh, I will. That's good that you say that. That's actually my next slide.
Oh, okay.
But with the machine learning stuff, it was 70,000 images. 70,000.
Wow.
Yeah, that was fun. But we overdid it. We even have in the paper, because it's like, when is enough, right? It's like Thanksgiving dinner, right? We keep eating and eating because everything's so good, but when should we stop? So we actually overdid it on the annotations to see where the learning curves were. That's why I did 70,000.
Thank you.
Yeah, you're welcome. Thank you. That's a great question.
Brittany, I have one question about how well this software or machine learning is distinguishing the image that you are looking at, the intensity of the stain versus how widespread that is, because it's a protein or something that you're looking at, right? So that's what I mean. I always was very curious. First of all, I mean, this is a very good piece of data. I mean, I really appreciate that you have you're presenting that to us. But I'm just curious that how this process of computerized system is learning about a protein that can express from a many different fold versus maybe 1 or 2 fold. I mean, it's a pathology versus the computational biology question, I would say.
So to rephrase, are you just talking about, just so I'm understanding your question, like how dark the staining is?
I would say, yes, you can say that. I mean, I was just curious, like how the machine or the software can see it. Okay, this is the extent of the disease versus this is just the starting of that particular.
Okay, so we're not there yet. So again, getting back to, and this is a great question to clarify. So again, we're dealing with tasks. So what you're talking about is more of a job, which will then be the synthesis of multiple tasks. So the first task that we're trying to do is just, can we identify a plaque?
Okay.
That's it. That's our question. We are now moving towards like more of the disease phases, disease stages for that. Like that's a second task. So trying to break it down, just like how if you have a team of 100 people, right, and you're running an Alzheimer's disease center, okay, one person's in charge of the MMSE, another person's in charge of this. So you have all these like little tasks. And so right now we're just at this. But to get at your maybe your color question, so looking at these, as well as we did run the data with and without color normalization, and the color normalization didn't really alter the AUC curves at all. So the tintoral properties of the tissue, which is a good thing, that's what we want from the generalizability, because you will have, especially with DAB staining, if anyone's ever done IHC, like this, there's, you know, the temperature in the room will affect it, right? That's why a lot of people move towards fluorescence, because it's more direct and you can measure, you know, the 1-to-1 ratio. With this though, it's more of the shape factor that we're finding that it's detecting in the surrounding area. So it's not just necessarily the core, but notice it's looking at these other objects too. And that's why I try to encourage people who are doing machine learning, just don't run the Python in this and get the AUC curves. Try to go the step forward and really get those grad cam feature occlusions. And there's even salience mapping and the heat mapping to get at that interpretability. This doesn't work with, say, like natural language processing. That's totally different. I'm saying if you're doing any sort of image analysis and machine learning, there's some methods that I think, when I think about this, should actually be standard. Like it's your checkbox of like, can you publish on this? Did you have this? Did you have this? Did you have this? Okay, you can be accepted, instead of just like, look, it works. It's 95% compatible.
That's, yeah, so machine basically is telling you whether it's a yes or no, versus what the extent, it's not the question.
Yeah, so the extent was the heat maps. So we can do this and get some quantification. So we are doing that just to provide that deeper phenotyping. So we do have this. And then I'm even having, I have another graduate student that's working on an algorithm, because again, just tasks, is gray white matter segmentation. Because if anybody's ever traced slides, right, like you're trying to do, it's a pain in the you know what. So we're even thinking from that standpoint is, can we have an automated process and just dump a whole bunch of slides in overnight, and then it comes out with a mask and there's your tracing of gray matter, white matter.
Okay.
Tells you how many plaques are there. But then this is that whole pipeline, right?
Thank you.
So these are great questions. Yeah, these are really simple. This is not, it is complicated science, but I like to keep my questions simple. Like, can we identify a plaque? Let's do that first. Okay, any other questions before I move on? Okay, so with that, somebody had a question of how many brains and stuff we have, and that's when I'll get into our resources. Yay, and we share, guys. Isn't that so exciting? So with formalin fixed tissues, we have that from over 300 cases. For paraffin embedded blocks, which a lot of people will cut into really thin sections, we have that in over 800 cases. Frozen brains, which people will use for like Western blots or RNA analysis, we have on over 500 cases. CSF is a little bit lower. We stopped collecting that just because we were getting a lot of contamination, so the quality wasn't that good. So we don't have a lot of CSF. I actually should probably take this off just because the quality, it was contaminated by a lot of blood. We are getting those microscope slides to share, so we can share, you know, if you want to have an image of a hippocampus of an H&E and do some quantifications, we have that. So we're scanning that in. And then we have some longitudinal samples, but this was started much later. So a lot of requests lately, a lot of people want serum, plasma, and brain samples from the same cases. Those are very limited because we've been doing our brain bank for over 30 years. With the blood, we just incorporated just a few years ago. So a lot of those patients that we have blood samples on haven't passed away yet, which is a good thing, right? They're still alive. So we don't have a lot of those. But this is just kind of our menu. So you can kind of see and do that. And like, I like to explain this to people is we can give you like the list of ingredients, but you're the chef, right? So we're telling you a lot of the stuff that we have, but you're having that scientific hypothesis, and we can come help you with understanding, can those be used for that or not, and understanding the limitations. And with that, we do have grant opportunities. And if you notice the state, this is just released. We are offering grants for developmental projects, and these topics include, and anyone can submit to my knowledge, right, for that. And this is, it's a pool of money, a total of $100,000 that can be split up to 3 projects, right? So it doesn't mean $100,000 for one project. It's just we have a pool of that, and we'll see what type of applicants we get for that. And so this is just some information. So if anyone was like, oh, I have this idea and I want to test it and I have to get some pilot data, this is the perfect avenue for that. And so with that, I took you on a journey of a couple different topics today. So I talked to you about the many phases of dementia and why they mattered in the way of the clinical presentation versus underlying disease. So people could have outward signs and symptoms, but what's in their brain. Talk to you about disease stage. People just don't wake up with dementia, it's a process. Concomitant pathologies, so people can have more than one pathology in their brain at a single time. Demographic variables and how they can affect disease presentation. Talked about the uses of machine learning to understand these. Talking about developing a pipeline, understanding how to manage those cross-disciplinary dialogues, and you have a start product and a finished product. How to get there, the interpretability, and then last but not least are resources. So I talked about those many faces, but again, back to the ones that got me started in this journey, is to understand these faces really can lead to better biomarkers, treatments, and model systems for all who are affected by the disease. And then there have been many faces, as you hopefully have seen throughout my presentation. Even though I'm here presenting, I couldn't be here without all the amazing people that I worked with. And I probably even forgot some people here because I was trying to make sure to include, you know how that feeling, like you're making sure you're trying to include everybody. But it's just been such a joy. And then if you want to be a part of this team, my laboratory has been looking for postdoctoral fellows to join to help with these great endeavors and these great questions. And with that, I can take any further questions.
Thank you so much, Brittany. This has been wonderful and a lot of interesting and exciting. But I want to open the floor for questions and comments from the audience.
Thank you very much. I have a question. That's a wonderful presentation, Dr. Ducker. It's really great, So I mean, with the machine learning, I mean, it's really a great promise, right? To be able to identify the diagnosis maybe much earlier than the clinician would ever kind of think they would do, or maybe try to define this comorbidity that you mentioned. How far do you think we are, from being able to do such a things?
I think we're getting there because we have the tools to do it, and they're getting cheaper. Just like how I equate this to when people were sequencing the genome and how expensive it was when it first started. Right now, GPUs are pretty affordable. I actually have a cluster in my lab that I'm able to run, which, I don't need. You think of, I'm trying to remember back in the day, a computer would take up a room, and all of a sudden we can fit it in the palm of our hand. It's an amazing feat how this is happening. So we have that. The issue is, though, back to some of your points, you were talking about full diagnoses. Again, I'm thinking of tasks. I'm thinking more of speeding up workflow and augmenting abilities rather than the end all be all. And I think that's a big thing to get across, is a lot of people have this fear that computers are going to replace humans. I'm just like with so many other things, you walk into your kitchen, there's a lot of appliances that have made our lives a lot easier throughout the years. I look at machine learning of making our lives a lot easier, not replacing us from that. So using the term augment. Does that help a little bit? I just wanted to make sure that's clear.
Thank you.
You're welcome.
And Brittany, is this technique applied to other brain disorders?
Mm-hmm. Yeah, so we looked at, even when we did our pilot study, we looked at, I'm trying to remember how many, I think it was 42 different types of cases that had a variety of diseases. So we just didn't look at the black and white. We looked at the whole spectrum. And even with the Emory cohort that we validated things in, that had a whole bunch of different concomitant pathologies as well. That's how we found the TDP-43 difference, we had enough cases to do that. Even though it's a very small study, it's still exciting that this can be applied, and other people have recreated that. And that's why I get so excited with this, is we released, that's another thing. We made all this stuff publicly available. So all our codes available, the images are available. So if you have somebody that is a computer engineer, you can recreate this maybe within a month or two, just depending on the skill set. You do need somebody with a computer engineering background. It's not something that you download an app, right? This is, we're trying to get to that point, but right now you have to have somebody that knows how to do Python and YOLO pretty proficiently to do that. But as you know, we're in these wonderful large institutions typically that might have a computer science department, that might have an army of undergraduates that you can be like, hey, guess what? I have a senior thesis project for you.
Hi. Hi, this is Camille. I'm a psychiatry resident. I just wanted to catch this opportunity to ask about Python. Do you know anything, like any kind of superficial purpose, what Python is specifically used for in that case? And is there any other program, as far as your knowledge goes, on computer engineering that a computer engineer should know about in order to do that work?
It all depends. The best way is just to probably team up with a faculty in computer engineering, because then they can gear you towards the students and then they can know the level of competence. And this kind of goes with trusting your collaborators. So I myself do not know Python. I myself do not know YOLO. I know some of the basics to carry a dialogue, to understand, you know, when things need to go. But yeah, there's a lot of different computer languages, and I would definitely make sure, if you're going to do this sort of endeavor, make sure you have somebody that knows that. But there's a ton of, and this is so great. We're in a time where so many undergraduates do want to get into medical imaging, and this can help them, again, from an educational standpoint, right? It allows them to get their foot in the door and have something that's table ready, and how can they expand it?
Could you talk?
Did that help a little bit? I kind of dodged the question politically.
Yes. No. Yes. Yeah. That's completely fine. I just wanted to kind of try to pick your brain if there's anything further. Some Python done on.
Yeah, and all this stuff is clear in the method.
The images that you're talking about.
Say again, you were
Yes,
kind of breaking up.
Yes, and the images that you're talking. Oh, okay. So I'm losing service. I'm in a not so good area, so I'm just gonna let other people talk. I'm just gonna let other people.
Yeah, feel free to email me. You can email me. It's okay.
Can you talk a little bit about the problem of this interdisciplinary work, in terms of how do you know when your computer engineer knows enough about the project to know what results you want? Did that make any sense?
No, it did. This is all about creating, and this is just my experience, and if anyone else has experience with, you know, multidisciplinary collaborations, I always try to create as transparent and safe an environment as possible, because that allows for questions. So if you have an environment like that, if somebody doesn't understand something, they feel more comfortable asking that. And the same goes for me, is like, they could flip your same question, they could flip it on me. Like, how do they know me as the pathologist that I'm telling them what they need to know? So it goes in the same direction. So you really have to delve deep, and it takes time to do that. I think the best phrase is, one of my mentors always said, you have a day to cut down a tree. How long are you going to sharpen your axe for? It's a great saying, because all in all, things do have to get done, but you have to try to think of, how do you move forward with that dialogue? And it really is and you have to constantly work at it. It's not easy. If somebody thinks it's easy, please give me hints of how to maintain that. Because there's not just the knowledge standpoint, there's personalities, there's different approaches to things, and how to do things in respectful ways that, you know, I respect the computer engineers and their expertise. They respect me and this. Okay, let's let's have a dialogue, just like how we're having now. I really appreciate all your guys' questions. This is great.
Thank you.
Did that kind of help a little bit, Michael?
Yes.
And I wanted to put you on the spot.
Oh dear.
Because we were.
Oh, my camera's failing. Oh no, I'm kidding. I'm kidding. I'm kidding. Okay.
So before initiating the talk, you were sharing with me that how much you value new ideas, and you were talking about citizen science.
Yeah.
Could you, just without going into any privileged information, sharing with us, how do you see the public role in the use of all this knowledge that neuropathology brings about?
I think it's a way, and we discussed this a little bit, is there can be knowledge, but then how do you make knowledge wisdom? From that standpoint of we're bombarded with knowledge every day. I think there's a statistic, and I'm going to butcher it, right? You just think of from the moment we wake up to the moment we go to bed, we look at our phones, we look at our emails, we look at so many different things of communication. Try to tally that up. That's probably thousands of pieces of knowledge, of information that our brains are absorbing. So with this concept of citizen science that you were trying to hint at, Gladys, is how do we stand out? How do we make sure that message is clear of what neuropathology is? And I think that's, again, a partnership issue where you bring people of that community that you want to reach to the table. It's a stakeholder issue. Anytime you're embarking on something, just like how you saw that dialogue, you want to start to think about every faucet that might touch and bring a representative of that area to the table so they have a voice. I don't know. I've experienced a lot of the conflicts that I experience have mainly been due to I haven't brought a certain person to the table in a timely manner. Romeo and Juliet, right? Let's even go back to literature. What's the root of that problem? Was information flow, right? They both died because information wasn't shared in an appropriate way.
Definitely. But thinking about the inside of the body, I'm just trying to think how much should we and perhaps marketing should help us, and linguistic and all that. But I'm wondering, talking about the brain is very different than talking from a lung or kidney or any other tissue. We see a lot of visualizations in TV programs for plastic surgery, and CSI type of programs also have shown us very gross aspects of our bodies, but really there is very few communication or public exposure for brain tissue.
To me, it's hard because I'm glad that you're saying that perspective, because for me, I'm so immersed in it. When I see anything brain related on TV, I get so excited. So for me, I'm just very sensitive for when it does present itself, because that's to me my field. So it's nice to hear your perspective that, from what I'm hearing from you, is you don't think that, or you haven't seen that the brain tissue is very prominent.
So people are eager or curious to see, like, again with the plastic surgery, how is that done, and that kind of stuff. But I'm wondering, and the gross and morbid of death and horror movies have shown a lot of chunk of human bodies. But I'm wondering, what kind of messages should we develop to inspire, to make people aware of the beauty of the brain, of the tailored and dedicated approach that allows you to do your work.
So is your question to get people for brain autopsy, or what would be the question? What would be brain health in general?
How do we get people to interested in knowing about really what's going on in the brain, and how can they use what they learn once they get to actually have a hint of what they see when they are exposed to brain tissue. Still, it's like I think, in my perspective, a whiteboard. What is there? What are those spots? What are those colors? It's my brain in colors. So we're still very distant from establishing a real dialogue about brain structure and impact of even diseases, but even more distant about uh, social disparities in the brain.
I don't have an answer for that. You know,
So
as a it's so interesting, and I love hearing your questions, because for my career, all of my patients are cases, so I don't even deal with living people. So hearing from you guys on your perspective and what you're telling me of, like, people don't know that much about the brain, it's awesome for me to hear that, because then starting to realize about this deficit. Because for me, I'm so immersed in my field, I think everyone loves the brain, which I should step back and realize people don't, right? You know how we all are. We're like, yes, everybody cares about what I care about. The study section cares about what I care about. But no, I'm so glad to have these dialogues with you, because for me, I'm learning too. So it's good to hear from you, Gladys, that, trying to be better of having people aware of their brains and what they're capable of.
Gladys, I in the classes I teach undergrad, I usually poll the students and ask them what their interests are. Neuroscience is always one option. It's a minority of students that have an inherent interest in the brain and neuroscience in general, to be quite honest. I think the vast majority find, like, if you ask them, what do you find interesting or fascinating? Most of, at least the students that are liberal arts, psychology, sociology, would gravitate more toward the clinical part and helping people. Like, the human interaction is what I have found that most find very interesting. About, like, the brain and inherent interest in the brain, I think it is a minority. We're also, and you're part of this too, I think, Gladys, right? I've always been active in, like, brain awareness activities. So, like, the Dana Foundation, Society for Neuroscience. And what I find is that the approaches that they're taking, also, it's trying to recruit people at the national level who have an interest in the brain. So how to, again, maybe I'm misunderstanding the question, but how to maybe engage more people? I mean, that's an interesting question, but I think that trying to get people to be more interested in the brain, that I think might be a little bit of a challenge, I think, because the inherent interest, I feel, is a minority of people. Of course, I haven't asked, what about the heart? Or what about this, or what about that? I mean,
you give a good point there. And so one of the things, just from my personal thing, even growing up, like I told you, is auto industry. So being a brain scientist wasn't even on my radar until I was in college. Imagine if I knew this, that when I was 5 years old, like, I want to be a brain scientist. What 5-year-old do you hear say that? And if they do say it, it's because they had an exposure. So back to the brain awareness, which is a thing that I've been doing now for quite some time, is I bring brains into classrooms. I will bring a human brain in a bag to a 5th grade classroom and just have them touch it. I won't even really lecture. I'll just have them touch it and ask questions. And that, to me, has such an impact with the students. You're not lecturing on it. You're just, like, showing it to them, having them ask questions. And then I bring in a whole bunch of different animal brains too, which is always hilarious, because they'll be like, the rat one looks different than the human. Why is that? I was like, why do you think that is? And you see them, they're like trying to think.
No, I think that's wonderful. And I've seen some of the reports of your activities in the website of Davis. I'm just thinking, like, nowadays you go to the gym and these coaches, fitness, or, whoever is next to you really know a lot about muscle biology. Oh, you should eat this, you should do that, and they talk to you about lactic acid and all that. I wonder, what it would take for brain science to be addressed like that. Do you know that's not good for you, or you should do that, or this is what's happening with the brain derived nerve growth factor or whatever?
Well, aren't we all on Prevagen, which is derived from jellyfish?
Meanwhile,
Sorry.
the industry is, you know, taking advantage of that ignorance. You know, and basically
Michael,
promising
are
a
you trying
brain.
to talk? Because I think you're muted.
Dr. Salom?
Oh, thank you. Actually, I have a question about your samples. You know, I mean, how well characterized these samples? Do you have like histories? I mean,
How do you define, what's your definition of well characterized?
Well, you know, their medical, like prior medical history, for example, if you have a, you know, an extensive history, you know, where do you have history on their, let's say, habits, alcohol use?
Yeah, that's a great question. So all these are part of the Alzheimer's Disease Center, and we have standardized forms that we use for a unified data set, and all those are available. And if you want to email me, I can send them to you. So we have like standard intake packets that have all the questions that they do over the years. And then I have, for Neuropath, I have a standard form I have to fill out that, you know, has all the variables. So all that is standardized. So we have cognitive assessments. We do have tobacco and alcohol usage, and that's typically gleaned, and it'll even tell you who it's gleaned from, whether it's gleaned from the subject or it's the informant questionnaire. So all that we have, and that's been standardized. And it's not just with our center. What's really great is we do the same forms that all these other 30 sites across the country do, and they dump them all in to what's called the National Alzheimer's Coordinating Center. So all that's there. And if you're I should have plugged. Gladys, I can send it to you. I actually wrote a stats book in my spare time on how to do some of these data, because they're pulled from multiple locations. And as you know, there can be confounders because you'll have center bias. And so we actually wrote a stats book to how to code in R, SAS, and SPSS, because all these, like, how do you even run? You have a large data set. How do you run frequency data in R?
Right.
Wow, awesome.
Yeah, so we're actually doing a webinar, I think, end of this month to talk about that. So I can send that to you, Gladys, if I haven't already, if you want to distribute. Yeah, and it's a stats book. It's like the fundamental statistics of Alzheimer's disease. I work with statisticians on this because even if you work with statisticians, you know that's a dialogue. And that's why the book came about, is because we were having such this deep dialogue of like, wait, what do you want for your output? Wait, what's the input? Okay, what? And we kept going back and forth. And then we finally just decided, after all this hard work, we're like, let's just write a book.
Wow, that's awesome.
So it was the student, it was her thesis. We took a PhD student's thesis and we turned it into a book.
Wow, that's wonderful. And please keep us on the loop for, you know, any of your talks, and keep us posted on how your projects
Definitely will. And the open scope will be this week. I'm having 2 of my students present on blood vessels. So if you're interested in learning about blood vessels, they're going to present. I'm making them they're not on the call, but I'm trying to, you know how giving presentations can be nerve-wracking. So I'm trying to teach them early. I was like, well, you're going to give the presentation at open scope.
Wow, wonderful. So I don't know if there is any other question or comment from our audience. I think this has been very, very informative, and you gave us much more to think about than a neuropathology of the
Well, you gave me a lot of stuff, Gladys. I love how your questions, like, people know everything about their muscles and their lactic acid, but why can't you go to the gym and somebody can have a conversation about, you know what, my brain, the acetylcholine levels today are just out of whack.
And I want to thank our audience from UTRGV, from our UT system institutions that are visiting us. And so very, very excited to have you. And please keep us on the loop, you know, any development, any research that you think eventually we are going to get there. You know,
you guys got to do the same. You guys got to do the same, because like I said, like, I'm a pathologist. All my patients are dead. They don't give me much information outside of what's in their brain, right? So hearing your guys' experience and stuff with your cohorts is truly, I think a couple of you have presented in our research seminar, which was really, really helpful. So Thank you guys. So
We
please keep the
eventually,
dialogue going.
it is in our plans to have the Institute for Neuroscience, Neuropathology. We are, a very young institution, university, and our chair, Dr. Salom, I think he even doesn't have 6 months with us.
Oh, wow. So your
Yeah,
first 100 days in office, everything's going okay?
so I'm so glad he is getting, all these ideas and to add to the catalog of things that he has envisioned for the Institute. So very, very thankful for your visit. I hope to have you here in person when conditions are, better. And thank you so much for
No,
being with
thank
us.
you guys and all the work that you're doing. Like you're right there in the thick of stuff trying to understand this precision medicine approaches. So thank you for what you guys do.
Thank you.